Okay, so now we're in module 10.2, and so now we're going to be dealing with two means instead of just the one. And don't forget, with means, it's a little more complicated. You have to know if you're dealing with a Z or a T procedure. In the previous section, we developed methods for comparing two proportions. Now we're going to do two means. So now our parameters of interest would be mu sub 1 and mu sub 2. Okay, so this is just like all the things that you could get out here going on, just like before. Okay, so in Chapter 7, we saw that one mean had to be approximately normal if n was greater than or equal to 30 by that central limit theorem. Or we could show a box plot, a dot plot, whatever we needed to if it wasn't greater than or equal to 30. Okay, or if the population isn't normal. The center is going to just be that mu going on. The spread is going to be your sigma divided by the square root of n. Okay? And you have to check your 10% rule for the whenever you're dealing with sigmas. Okay, we're going to go ahead and jump ahead. So here would just be like a computer output. So you can see the shape. If both of them are normal, then you're going to have the difference that's normal. Your centers, all you have to do is subtract. And when you're dealing with the spreads, you're going to have to do a little bit more. We know that with the spreads, we're going to have to use the variances. Okay, so just like we were dealing with means, here we can see we're going to square the standard deviations for both the samples and then take the square root of the sum. All right, so the shape is going to be normal if both of the populations are normal. If we don't know that, then we're going to have to see that both of the samples are normal, and if we don't know how that, then we're going to have to investigate with a graph, and I like to use the box plot. The center is just going to be mu sub 1 minus mu sub 2. And the spread is going to be the square root of both of the variances squared, adding them together. And we have to check the 10% condition for that. So here is just a graph of everything in summary. All right, so let's do this example. Who's taller at 10, boys or girls? Based on information from the U.S. National Health and Nutrition Examination Survey, the heights in inches of 10-year-old girls follow a normal distribution with a mean of 56.4 and a standard deviation of 2.7, and the heights in inches of 10-year-old boys follow a normal distribution with a mean of 55.7 and a standard deviation of 3.8. A researcher takes independent samples of 12 girls and 8 boys of this age and measures their heights. After analyzing the data, the researcher reports that the sample mean of boys is larger than the sample mean of the girls' heights. All right, so let's describe the shape, center, and spread of what's going on. Since both of the populations were normal, it told us that they both follow normal distribution, then we know the difference is going to be normal. So we can say the mean is the mean of the girls minus the mean of the boys. Our standard deviation, we can take the square root of the 2.7 over the 12 squared plus the 3.8 over the 8 squared. And you're going to get out 1.55 inches. So find the probability of getting a difference in sample means that is less than 0. So here we can convert back to z-scores. And we can use the table to find that area. Or we could do our normal CDF to get an even more exact area. So does the results in this part B give us reason to doubt the researchers' stated results? So if the mean height of the boys is greater than the mean height of the girls, that is that the girls minus the boys would be smaller than 0, or the boys minus the girls would be greater than 0. However you'd like to set that up, it's kind of up to you. Part B shows that there's about a 33% chance of getting a difference in sample means that's negative just due to sampling variability. So that could happen. Okay, 33% chance is fairly large, so this gives us a little reason to doubt the researcher's claim. Okay, so when we have two samples going on, in general, if we don't know the population, what we can do with the samples, very, very similar to what we were doing with proportions. But if we don't know the standard deviation of the population, then we're going to have to use a T sample now instead of a Z sample. Okay, so that's the biggie here. So here, when the random, normal, and independent conditions are met, for a T interval, you can set it up with your difference of your sample means, plus or minus your T star, times your standard error here, checking all three conditions. Okay, so let's look at this one. The Wade Tract Preserve in Georgia is an old growth forest of longleaf pines that has survived in a relatively undisturbed state for hundreds of years. That'd be awesome. So one question of interest to foresters who study the area is, how do the sizes of longleaf pine trees in the northern and southern halves of the forest compare? To find out, researchers took a random sample of 30 trees from each half and measured the diameter at breast height in centimeters. Comparative box plots of the data and summary statistics from a mini-tab are shown below. Construct and interpret a 90% confidence interval for the difference in the mean of the DBH for longleaf pines in the northern and southern halves of the Wade Tract Preserve. Okay, so let's first look at it by hand, and we could also look into the calculator. Okay. So here's our N, our mean, our standard deviation, and you can see by the box plots the shape. So let's state our parameters of interest. Our mu sub 1 is going to be the true mean of the DBH of all trees in the southern half, and mu sub 2 will be the true mean of the DBH of all trees in the northern half. So we're going to estimate the mu sub 1 minus mu sub 2 at a 90% confidence interval. So in this case, since the population standard deviation was not known, we're going to use a two-sample T interval and check our conditions. It said that they were both random. 30 was, so since both were 30, then we know it's normal, and even if they weren't, we could look at the box plots to see what was going on, but we're good with the central limit theorem there. Independent. It said that they took independent samples from both the southern and the northern halves. So let's see, since we're sampling without replacement of 10 times 30, that's 300 trees. So this is pretty safe to assume. It's a big forest here. So since the conditions are satisfied, we can construct our two-sample T interval. So we know our mu sub 1 minus mu sub 2. We can look in our chart for our T star. Degrees of freedom would be 30 minus the 1. And we're at a 90% confidence interval, and I always go up from 90 up. And your degrees of freedom to the right, so that would be the one that you'd want here. And then you can, what do we say? Oh, mu sub 1 minus mu sub 2 was right here. So there's your mu sub 1 minus mu sub 2, and you can simplify that down. And then you have your T star times your standard error. And when you simplify, you can get your interval. So here we are 90% confident that the interval from 3.83 to 17.83 centimeters captures the true difference in the actual mean of DBH of the southern trees and the actual mean of the DBH of the northern trees. Okay. So let's look if we had done it in the calculator. We could go to stats test, and in this case we're going to be doing a two-sample T interval. And here you can see the sample. You're never ever going to choose pooled again. I kind of stated that this is complicated. We don't have to worry about it. So always just choose no. Okay. So this interval suggests that the mean diameter of the southern trees is between 3.83 and 17.83, larger than the mean diameter of the northern trees. All right. When is no different, and your alternative you can have greater than, less than, or not equal to. If you'd like to set up your t-score, and then you can find that p-value using your degrees of freedom in your chart, or you could use technology. I'm going to use technology just to always just set up my test in general, though, doing my my 2 sample t test, or 2 sample t interval. In this case, we're doing a test. Check your conditions. Random, normal, independent. Maybe. Come here. All right. So you guys should be good to go with that. So here is, in general, if you like to always use the formulas, that's fantastic. Otherwise, you can use your calculators. So let's look at this example. Calcium and blood pressure. Does decreasing the amount of calcium in our diet reduce blood pressure? Examination of a large sample of people revealed a relationship between calcium intake and blood pressure. The relationship was strongest for black men. Such observational studies does not establish causation. Researchers therefore designed a randomized comparative experiment. The subjects were 21 healthy black men who volunteered to take part in the experiment. They were randomly assigned to 2 groups. 10 of the men received a calcium supplement for 12 weeks, while the other control group of the 11 men received a placebo. It was a pill that looked identical. The experiment was double-blinded. The response variable is the decrease in systolic top number blood pressure for a subject after 12 weeks in millimeters of mercury. An increase appears as a negative response, and here are the data. Okay, so let's state our hypothesis. We're going to say that mu sub 1 minus mu sub 2 is their equal, or their difference is 0. Our alternative, here we want to know if there was an increase. Okay, and make sure you state what mu sub 1 and mu sub 2 are in context. So we're going to do a 2 sample t-test because we do not know the population standard deviation. But first we have to check our conditions. Said it was random, normal. With a small sample size, we need to examine the data to see if it's reasonable to believe that the actual distributions are normal. So here I'm going to make a box and whiskers plot. And then you could have picked other things, but I looked at for both populations here. And both of them look fairly normal. Maybe some slight skew, but fairly normal. So we could go ahead and assume that they are normal. Independent, the random assignments of these 2 groups of men can be viewed as independent. Okay. All right, so the non-calculator method, we setting up your t-score, looking in your table, and getting a p-value that's between 0.05 and 0.10. I'm going to jump ahead and then come back. If you put it in your calculator, then you're going to have to enter all of that data into your list 1 and list 2 now. So you're going to do a 2 sample t-test, but you're going to be using data instead of statistics. Okay, so when I got my p, I got it to be 0.0644. Oops, wrong way. And 0.0644 was between 0.05 and 0.10, but it's a more accurate method. So this is not statistically significant because our p-value is greater than 0.05. So we're going to fail to reject the null hypothesis. Okay? And then state in context of the problem. All right, so let's look at this example. Let's say that I had this. Again, this is just all putting it into the calculator if you want to see in more detail. And yeah, still have to check conditions, all that fun stuff. Yay! Still have to state what mu sub 1 and mu sub 2 are in context of the problem. Just that instead of using the chart, you can use your calculator. All right. See how you do on this one. And unpause when you're ready. All right, just some notes about using the two sample T procedures wisely. I'm going to let you read through these. So if the data is really, really, really skewed or you have outliers, you should not use the T. Choose equal sample sizes if possible. Do not use pooled. Make sure you're not doing a paired data, because that would just be a one sample. And here's your summary. So, it kind of says, lots of the summary, right? It says, are you confused when to use what test yet? So this is going to help if you go to this website, and I have this listed in the module too. So on this website, they're going to give you a problem, and you have to say which one you think it would be. So you could say, oh, I think that. Try again. And you can say, oh, I think that. They can tell you. Oh, they give you a hint. Try again. And once you get it right, you can keep moving on, and they'll give you new examples. Now these two down here, you do not know yet, the chi-squared. We're going to get to that in the next module. So if you get one of those, sorry right now. But if you wanted to start practicing this is a really good website. Oh, resume slideshow. Okay, so we only have chi-squared left to go with all of the tests. So then I just have some old AP questions if you want to kind of practice some of these. You can work through them and see how you do. Hopefully it's pretty straightforward. And you can pause and go on when you're ready to check your answers. Here's another one. And when you're ready to go on, you can pause to check or unpause. And if you want to do any of these with me, we definitely can. Just let me know. And this is all how AP would be grading it to get correct points. Okay? So you made it through Module 10. And I will see you in Module 11 when we do chi-squared. Only 2 more left to go. Woohoo!